Swayam Prabha. Digital India. Educated India.
So hi, welcome back. So we were trying to set up the mean momentum equation over a grid. So that is essentially the basis of computational fluid dynamics, right? And so let us continue to do that. So we had a grid which we set up in this fashion right here, and we were writing out this equation, right, the mean momentum equation given by here 1. Right, we were looking at this equation, and we are trying to see how we're going to solve for the mean velocity using a grid like this, right? And so we set it up, and we basically said that these derivatives that we have here, right, second order derivative in x, second order derivative in x and y, and a first order derivative for the pressure. So these derivatives can actually be written in terms of the function values, which in this case is the mean velocity at various locations. Now these locations are the ones which we are tracing out, or which we are locating, so to speak, by the intersection of these grid lines, right. So this is the basis of CFD, and we have essentially a Cartesian coordinate system. So this domain is in a Cartesian coordinate system, which is rectangular, and the length, what to say, in the x direction, the length is the size of the grid, so to speak, is delta x, and in the y direction is delta y. They don't have to be same, but they could be, right. Okay, so that's what we were writing out. So for example, this one, so if you had to write the pressure, so the gradient of the pressure in the x direction at location 0, okay, which is this. So it essentially means you take the pressure value, mean pressure value at location 3, and subtract that, and that subtract P7 from it, the mean value of the pressure at P7 from P3, divide that by 2 times the grid size, which is 2 delta x. So that's what this is this is a central difference formula, right, for the first order differential, in this case for pressure in the x direction, right. And then we have a second order differential, which is here, okay, of the mean velocity. Again we take that at O, which essentially means that I take the function value, which is the mean velocity value at 3, add the mean velocity value at 7 to it, and subtract 2 times the mean velocity at 0, and divide by the grid size squared, right. This essentially gives me the second order derivative here, right. So again, now the second order derivative in x and y, right, again at the location 0, basically turns out to be these diagonal elements, sum these up, the function values, which is u mean at location 2 and at location 6, sum that up and subtract the mean values of velocity at locations 4 and 8, right. So which is what we have here, and divide that by 4 times the grid size in x and y. Okay. So then we essentially wrote out basically we said momentum is conserved, therefore the left hand side goes to 0. So then we come up with the equation which kind of looks like this, right. So the left hand side, so we have a left hand side where we have all the unknowns, which is the velocity means, right. This is what our unknowns are, and the right hand side we have the pressure means, okay. So we wrote out this equation. The first one was at naught, okay, the location was naught. The second one we wrote out the equation at position 3 and then 7, which is essentially saying I wrote the same equation at location 3 and location 7. We did that, Okay. So we did that. So now where we are, so we will go ahead and look at two other positions, which is one is at 2 and one is at 10, because there we would want to look, because these 2 points are at the boundary, and like I said in the last class, that if I have to do, for example, a central difference of the variable at location 2 in the y direction, then I need a location which is beyond the domain, right? So if I use a central difference scheme, so then how do I go about this? So one of the ways of going about this is use a backward difference or a forward difference, which is what we will do here. And so similarly, we'll take one on this boundary, which is location 2, and the other on this boundary, which is location 10. Right. So which is what we started doing last time, and we kind of wrote this down and we stopped here. So regarding this location, okay. So let us see what this means, and we'll go ahead and continue from there, right. Okay. So I think the best thing to do is sort of right. Let's write down the equation. Okay, let's write down the equation. That's best. So okay. Right, this is the mean momentum equation that we are trying to solve here. Okay. Okay, so now that we are at location 2, then how do we go about this? So we're basically saying okay, so I'm basically saying that okay at the location 2, right. So this is equal to okay, the second order derivative in x direction at 2. So this should be actually, using a central difference scheme, should be equal to the function value at u12 minus 2 times the function value at 2 plus u1, right? Okay, that then okay. Now let us do something here. Let's just say this is essentially del del y. Okay, then the first order derivative of u mean in x direction, right? So x direction, so that in using central difference scheme is essentially u12 minus u1 by 2 delta x. Okay, minus 1 by rho, first order derivative of the pressure in the x direction. So that is P12 minus P1 by 2 delta x. Okay, and as we saw from earlier, this part goes to 0, right? So therefore we can essentially write nu right Okay. Now, del del y of u12, right, u12. Now, in the y direction, now I do not have a, if I use a central difference scheme, right, then I will need a point. So, I am at u12, right here, 12. Now, if I have to do a derivative of the function at in the y direction at 12 using a central difference scheme, then I would need a function value outside of the domain. So, which I can't do, right? I don't have. I want to remain in the domain, within the domain. Then what should I do, right? So, I could do a backward difference formula, right? I think that would be good. So, I take the function value at 12 and function value at 13. Okay. Okay. So, then at 12 is essentially my the thing is, so at 12 it becomes the function value, the backward difference is this minus u13, okay, by delta y. Okay, so that is for this is del del y of this is actually del del y, right, of the function at 12, right, this. Okay, then so same thing with u1, I also do not have, so I am going to use a backward difference formula, and this will be u1 minus u0, okay, by delta y. Okay, so again this is del del y at u1. Okay, and finally my equation, because I have taken the left hand side to be equal to 0, so this is equal to 1 by 2 rho delta x, right, into P12 minus P1, right. Okay, so I'm going to just sort of dress this up a little bit and write that out, or u12 okay, plus nu t by 2 delta x delta y into u12 plus this minus u13 minus u1. This is equal to 1 by 2 rho delta x p12 minus p1, right. So, this is particular equation. So, let's call this as, say, okay, okay, so that's essentially the writing out the equation at the location at the top wall, so which is basically 2, right, at the location 2. Okay, then let's go ahead and look at the wall, another point on the wall, which is, say, location 10, right. So essentially what I'm saying is d dt of u at location 10, right. So at location 10, So we have nu and the second order derivative of nu. Okay. Now, so we have a second order derivative in the x direction, right? And if we use central difference scheme, then we will not be able, we will need a point which is outside of the domain, right? Because I'm at the boundary now. So I'm going to use a, let us see how we do that, right? So we have this term del, so essentially what I'm saying is, so you have this term here, del 2 del x2, which is at the left wall. So I need a second order derivative of this, okay? So let's just say that this one is, so what if I write it this way, is nu, okay, del x, okay, del x of gradient at 10, right? So at 10, so I'm going to use a forward difference scheme here. I'm going to use a forward difference scheme here to get the derivative, first order derivative at 10. So I'm going to just say u7, right, minus this by delta x. Okay, then plus nu t, right, nu t. So essentially we have the next term is this, right? So let's just say first we'll go ahead and calculate the so del this one, let's just say it is del x. So the first order derivative in the y direction at 10, right? Here I can use a central difference scheme, no issues, right? I can use that. So let's do that, first order derivative. So that's going to be u11 minus u9, right, by 2 delta y. Yeah, and minus 1 by rho, okay, so minus 1 by rho del p del xj, minus 1 by rho del p del xj. So derivative, first order derivative of the pressure in x direction. Okay, so in the x direction again, so I'm going to use a forward difference scheme. So it is P7 minus P10 by delta x. Okay, this again as we have seen earlier, so this is going to go to 0. So therefore we can write, okay, so let us do this now, nu by delta x, right? So I have del first order derivative of the function value at 7, right? Now for this I can use, so what I'm saying is I have now a del x of u7, so function value which is mean velocity value at location 7, right? At location 7. So if for this I can use central difference now, because I have, it's at the domain and I have appropriate number of domain values. Is that right? Okay. So then u7, for u7, then it is first order derivative. So this minus u10, right, by delta x. Yeah, this, and minus again u10. Okay, now the first order derivative at u10, again this is on the wall, so I'm going to take a forward difference value. So here it is u7 minus u10, okay, by, okay, this one is 2 delta thing and this one is delta x. Okay, this plus now t by 2 delta y. Now again I need the first order derivative at location 11. Again 11 is on the wall, so we will use a forward difference formula. So which is U8 minus U11 by delta x, right, minus U9. So U9 again. Okay, U9 is also on the wall. Okay, so U9 is also on the wall. So I again use a forward difference formula, which is U6 minus U9 by delta x. Yeah, okay, right, and that is equal to 1 by, I think P7, this should be, okay, P7, this was the first order derivative, I mean forward difference method, right, P7, P10, right, okay. Now, so I'm going to just dress that up, okay. So what I have is u by 2 delta x square, okay, into, okay, so u0 minus u7, okay, plus nu t by 2 delta x delta y into u8 plus u9 minus u6 minus u11. This is equal to 1 by rho delta x p7 minus p10. Did I do that right, or did I sort of make a mistake? Okay. Nu by 2 delta x squared, this thing. No, I think I'm right. So what I got here, okay. So all right, so that is, therefore, let's just call that equation 3, 4. I think this should be 5. Okay, so let's call that equation 5. Okay, so now we have all these equations lined up. Okay, we have this equation, right? So we have this equation which we wrote out at, location 10. Then we have this one which we wrote out at location 2, and we have these which we wrote out. This one we wrote out at 0, this one we wrote out at 3 and 7. Then what do we do with this, right? So what we now, to sort of set this up, what we do basically is write this up in matrix form. See if we can do that. Okay. So we will write this up in a matrix form. Okay. So if I had to write this in matrix form, so what exactly I'm talking about? So essentially, let's just say, I have written just 4 equations, I think, right? 4 or 5. Yeah, I've written just 5 equations. And if you look at the domain here, right, I've written out 5 equations. But if you look at the domain here, it has essentially 15 locations, right, 15 locations. And essentially, using this CFD method, I'm supposed to calculate the function values, which is the mean velocity values at all these locations. But right now, I have just 5 equations. So the point is that we write out the equation at each and every location. That's what we do. Okay, so we do write out that equation at all locations, and then let us see if we put that in matrix form, how does that look, okay, which is what we're doing right now. So although right now I have written it out only at 5 locations, but what we need is essentially 15 locations, so 15 equations. So 15 equations and how many unknowns? 15 unknowns, right? So then that's going to give me a solution, okay, the way I've written that out. Okay, so now writing this in the so I'm going to try and do this as best possible. So essentially, what are my unknowns? So my unknowns are U1, right, U2, U3, U4, U5, U6, U7, U8, U9, U10, U11, U12, U13. Okay. All right, sorry. Now I need to, okay, I'm going to, erase that because I need to write U0, which I forgot. Okay, so essentially it's going to be U0, okay. Then you have U1, U2, U3, U4, U5, U6, U7, U8, U9, 10, 11, 12, 13, and 14. See, I'm almost running out of space here. Okay, so I'm going to put that in a okay. So bear with me, please. All right. So if I do that, and then, so you'll see what am I trying to do here, okay, and that should give you an idea. Okay. So this is just my left hand side. This is just my left hand side. Okay. So I have 2 matrices. So the right one that you see here is of the size, or I'm going to just write this here, that is essentially 15 rows. This is of size 15 rows into 1 column, right, this one. So therefore, this left matrix that I'm going to fill up very soon, so that one should at least be something into 15. Right, so that we will get, an equation. So if I have 15 equations, so I will actually, this will actually going to be 15 cross 15. Okay, this left hand side. So then what I will get out of this is a 15 by 1 matrix, right? So then I will have the right hand side, which is essentially the pressure terms. Okay. Now so what do I do now? Okay, now U0. So we wrote out that our equation at U0. Right. So let us go to each equation and just write that out in this matrix form. Right. So the first equation that we had, right, is this. So the first equation that I had was this. This one, right? This is the equation. Right. So what is the coefficient of U0? So what I can see here is minus 2 nu by delta x square, right? That's the coefficient of U0. So let's go ahead and enter that. Okay, let's go ahead and enter that. Okay, So, it is minus 2 nu by delta x square. So, that if I multiply by u naught. Okay. What is the next one? Okay. So, u1. So, there is no entry for u1 here. Okay. So, if you look at this equation, there is, if you see this equation, there is no entry for u1. So, what happens to the coefficient of u1? It is 0. Let us go back and write that first. Okay. So, u1 is actually going to be 0. Okay. So, next is u2, right. So, let us just see if we have u2 here. Yes, we do. So, u2 is one term which is nu t by 4 del x del y. Okay. This one, I mean if you see here. So, this is the u2 and the coefficient is nu t by 4 del x del y, right. So, we are going to write that here. So, it is nu t by 4 del x del y. This is for u2. Then let us go back and see what is u3, right. So, u3 also is nu by delta x square. Okay. Then u3 is square. Okay. Then u4, do we have a u4 here? Yeah, we do. So, it is minus nu t by 4 del x del y. Okay. Okay. So, this is not 1, 2, 3, not 1, 2, 3, 4. So, let us go and see what we have for u5. We actually do not have any anything for u5, right. We don't. So, u5 is actually 0. What about u6? We do have that. So, u6 is actually here, which is nu t by 4 del x del y. Okay. So, then this is nu t by 4 del x del y. Okay. This is, so not 1, 2, 3, 4, 5, 6. So, let us go look at u7. So, yes, we do have u7 in fact, which is nu by del x square. Okay. So, this is u7, coefficient being nu by del x square. Okay. So, then u7. Okay. And then we go and look at nu 8. So, nu 8 is minus nu t by 4 delta x delta y. So, it is minus nu t by 4 delta x delta y. This is 8. Okay. And then you see 9 to 14, there is nothing, right. So, there are no terms from 9 to 14. So, all of these are going to go to 0. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. Okay, so these are the 14 points. So, that is it, right. This is from the first equation. Okay. So, now similarly now that I have entered this, so essentially what this means is the left hand side of that first equation, that the difference equation now is essentially this into u naught plus this into u2, right, this into u3, this into u4, 6, 7, 8. right. So this is equal to the right hand side. We'll write out the right hand side. Well, we can write out the right hand side. So the right hand side okay. Now the first equation right hand side, okay, let us see. So if you see the first equation right hand side, it is essentially 1 by 2 rho delta x P3 minus P7, right. So this is let's just take that out and we'll say this is P3 P7, okay. This, okay, that's the right hand side. All right. So now if I go back, okay, and populate this thing, right, I'm going to populate this thing. So essentially now you know how I'm setting this up. So then you look at this again. If I go back, so this is the second equation, right, and again I look at these values and I just enter it there. Okay, let's do that. So again here this is u naught is nu by, you can see here in this case u naught is del by del x square, okay. So this is, okay, now wait a minute. So this one is for at the location of the point is 3 and 7, okay. So we can do this. So but we've also come up with at 2, right. So this one is at 10 and I think this one is at 2. So let us go ahead and enter this equation first, okay. You can, there's really no order in order to do that. There's nothing, you can just write anything, but I'm just trying to maintain an order for my bookkeeping, that's all, okay. So I'll just go ahead and enter the second equation first, okay. So it's at 2, it's at 0 naught, the first one, and next one is at 2. So in this case, let's see, if do we have a naught? Yes. So which is nu t by 2 delta x del y. Let's go ahead then. So nu t by 2 delta x del y. Okay, that is u naught. Then here, then u1 is minus delta t by 2 delta x delta y. Okay. u1 is minus nu t by 2 delta x delta y. Then u1. Then u2, yeah, u2. Okay. Now, as a matter of fact, when I do u1, it is minus nu t by this. I also have another entry, right, which is plus nu by del x square. Okay, so u1 is going to be that. So plus nu by okay. This is for u1, okay. So if you go here, okay, no. So if you're here, you can see that u1 has an entry where it is minus nu t by 2 delta x delta y, right, plus, okay, nu by delta x squared. So minus nu t by 2 delta x delta y plus nu by this. This is 1, okay, all right. Then if you go to 2, right, let's go to 2, and that is minus 2 by delta x squared. So this is 2, then Do we have a 3? We do not have a 3. We do not have 3, 4, 5, 6, 7, 8, 9, 10, 11. We just have 12 and 13. Right. So let's set it up with zeros. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 12, 13 and 14 is also 0, right. So we have one for 12. So the 12 is again an addition. So nu by del x squared plus nu t by this, right. So 12 nu t by 2, okay, and this, okay. So the 12 is nu t by 2 del x del y plus nu by delta x square. Okay, that is for 12. Okay, and now 13 is minus nu t by 2 delta x delta y. Okay, that's all we have. Okay, is minus nu t by 2 delta x delta y. That's it. Okay, so that's equation 2, which is, you know, set up. Okay, then let us go to, so we have this equation at 3. So let's set that up. So that again here we have nu by delta x square, that is for nu 0, okay, nu naught. Okay, so nu by delta x square okay, and I'm going to just write this out. Okay, so you can cross check if I've done this right. You can please cross check. Okay, you should actually. Okay, one, two, three, 6. So 1, 2, 3, 4, 5, 6. Okay, then okay, okay, so that is for the third. Then I have one for 7 and I have one for 10, right? So let's go for the 7. Okay, so for the 7, so essentially I will have several entries here. So 0, this was 2, this was this. So I will have, you know, other entries here. So I'm going to just write the 7, right? So the 7 is okay, nu t, okay, nu t, okay, 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 all right, and finally I will write out the equation here, which is here, right. So this one is, so again I have u naught, which is nu by 2 delta x square. Okay. So nu by 2 delta x square. Then do we have anything for 1? We don't have. So 1 to 5 we do not have anything. 1 to 5. Okay. So 1, 2, 3, 4, 5, and then I have a 6. I have a 6 which is minus nu t by 2 delta x delta y, nu 6, okay, which is minus nu t by 2 delta x delta y. U7 is minus nu by 2 delta x square. This is U7. Okay, then we have ut, which is U8, which is nu by 2 delta x delta y. So this is not 1, 2, 3, 4, 5, 6, 7, 8. So we go back, look for U9. U9 is nu t by 2 delta x delta y. So you had U8 and U9. U8 and U9. Okay. We don't have a U10. We'd have a U11 though, which is minus that. Okay, and rest everything is 0. Okay, so we have this and minus nu t by 2 delta x delta y. So 11, 12, 13 and 14. 12, 13, 14. So we essentially got not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's it, right? So we've got all our 5 equations into this, right? So, but I should mention here that right now, only 5 equations. Okay, all 15 need to be entered into this matrix system, right? So let me just complete that on the next page. So I got something for this was not, I had something for U2, right? So for 2, so that was, so this one is for 2, which is P naught 12 minus P1, 1 by 2 rho delta x, P12 minus P1. This is okay. So this one is essentially rho. This is 1. Actually, this is for 0. Let's just write it like that, 0. Location, right? 0. Then not, right? So we'll need an entry here. We'll need an entry here for 1. This entry is for 2, right? We don't have anything for 3. Or yeah, we actually have something for 3, right? Yeah, we actually have something for 3. Yeah, so we have this with this P13 minus P0. So U3. So U3 is P13 minus P0. Okay, this is for 0.3. We don't have anything for 4. Then we have something for 0.7, I think. Right? So that is for 7, which is P0 minus P10. That, okay? And finally, we have something for 10, right? So which is yeah, so this is 10, which is P7 minus P10 1 by rho delta x, so 2 times actually P7 minus P10. So it is P7 minus P10, but this is multiplied by 2 because it is 1 by rho delta x. I am going to just cross check the 2 whether that is fine. This is for 10, this is for 2 is fine. Okay. So you see how we set this up. So here this also is a matrix which is going to be 15 rows in 1 column, right. What I have in the left hand side are 2 matrices, right. So 2 matrices, when I multiply them, so the left hand side matrix is 15 by 15 and the right hand side matrix is 15 by 1. So if I multiply them, it results in a 15 by 1 matrix, which is equal to the right hand side matrix, which is also 15 by 1. Right. So then we basically numerically solve these. This is your CFD setup. So you set this up in this fashion. Okay. All right. So I will stop here and we'll take up something in the next class. Thank you.